think we can start. It's actually past 12. We have about 7 people that joined, so hopefully there will be more people joining soon. So today is lesson 9, so we're almost there. Once we finish that, it's going to be 3 more lessons and we're done. That was another interesting lesson, quite busy one as well, but that's good. So what I want to do, I want to go through the so the lesson 9 was supposed to be about regularization, learning rates, and NLP, but I didn't see any of NLP. I didn't see that much of the regularization as well. There was something about learning rates though. Right, so I think what I'm going to propose, I would suggest I have a couple of slides that I've basically copied from the that Medium post with the lesson notes. I think what I'm going to suggest to do, so we're going to say discuss on each slide as such. We're not going to wait until the end. So if anyone's got any questions or anything to add on each slide, that's how we're going to do it, I think. It kind of worked best last time when people did it, and I think it's good. So on this slide, what I just have is that how to create the neural network, basically one layer network, which is a logistic regression using the PyTorch NN library, the neural net library. So once we import all the Fast.ai stuff and once we import the torch.nn, we could assign the nn.sequential to our net variable, and then we could define the first layer, which consists of the 28 by 28. That's our image size, 28 by 28 pixels, because we're talking the MNIST dataset again. And then we want to have as the output 10 digits. So then the output layer is 10. And after that first layer, the next layer is the log softmax. And this is to kind of get the prediction for the number represented in the image. And all of that is on a GPU. So this is .CUDA. So to make it work, we also need to define what our loss function is. And we're again using torch NN module, NLL loss. Also define our metrics. And in this case, we want to see our accuracy as our metric. And as our optimizer, so instead of just basic SGD, we use the Adam optimizer. And with all of those defined, we could call the fit on that network, the data, number of epochs 5, the criticality is our loss, optimizer is our and metrics, our metrics. And that should give us I think as Jeremy showed, that gave like 91% accuracy. So just one layer, which is logistic regression, gives already quite good result. So I'm going to open for any comments, questions. Anyone found something interesting or not interesting or funny or anything?
No, I think there are probably going to be questions further down, I think.
Okay. Yeah. So the next thing, so once he did that, he started using the less and less PyTorch to create the same thing. So with using the object-oriented program in Python. Yeah, so without PyTorch, we define so we need to get the weights. So initially there are no weights. Well, if we don't use PyTorch, we need to initialize weights. So in this case, we're using the torch random function to create those randomly initialized weights. and also the definition of the softmax, also using some torch functions. And
so
then,
I have a question for you here. So I haven't come across this thing, you know, where the parameter for the get weights is this asterisk and dims, right?
mm-hmm.
Do you have any idea what that means? Because I haven't come across that in Python before. So how do you interpret that?
I'm not so sure either. Maybe there's anyone on the call who's familiar with that, and I'm going also to look at the chat. Let me see, how do I see chat? Oh, there is something in the chat. On the chat, there's a question whether slides are available. I will post them just after the meetup to a Slack. So we're trying to find out the get weights, and there's the star dims. Why do we have that star in the parentheses? I'm not so sure, to be honest. I'm not so sure why he used that. I was trying to look at the code to see what would that make sense, but interesting. I'm not so sure. Something we could. So on the chat we have just like star arg, and what the star arg? What I mean? Let's see if someone responds. Now I think that was also a question on the chat. So if it's something we need to maybe look up later, I'm not so sure.
Okay, yeah, no worries.
Yeah. If there's anyone on the call now who kind of wants to add something to the discussion, more than welcome. Okay. On the chat, we get this is list of arbitrary elements. If we had Christian on the call, he would tell us, but he couldn't make today. So yeah. Yeah, okay, there's a link. We could have a look at the link. Let's see if that loads. Yeah, asterisks in Python, what they are and how to use them.
I never use them. I looked it up before, and I just looked it up again. I think this is to pass iterable arguments, but that's just what I've read there.
Okay, yeah. It's a good stuff. So when you look at the thing at Jeremy codes, it seems so easy, and then you kind of discover things that kind of interesting. Yeah. Right. So it says that, for example, print asterisk fruits is passing all of the items in the fruits listed in the print function call as a separate arguments without us even needing to know how many arguments we are in the list. Okay, so I guess what it means is that there could be more arguments passed to that function. And that's what we're doing. So we passing the get weights. We are passing 2 arguments. One is 28 by 28 and another one is 10. So we didn't have to specify that that we have 2. We just put there's asterisk dims, and it basically you can pass. Yeah, it's a good point. You can pass as many as you like, I guess, without specifying that you need 2, 3, or 4. Does it make sense?
Mm-hmm. Thanks for whoever sent out that link. That's
yeah.
Sure.
Yeah, that's great. That's great. Yeah, I don't see the chat. Let me. So the more interesting, another comment from chat, more interesting is themes in brackets 0. What that denotes? Where is this? Let me see. Oh, right, yeah. So there's in the first line, in the return.
That must be your first one, right? The first argument that you're sending. If you're sending across the whole of the stuff, that must be the first.
So you're saying this is the first argument in the, yeah, so that's the 28 by 28 in this case, right? Yeah, I think so too. I think that would be the first argument that you pass, in this case, 28 by 28. Does it make sense? Sabu, who has the question? I think so. Yeah, thank you. Yep. So where were we? So what we're defining is, so we define the get weights. So because we want to initialize the weights, and we're defining the softmax function, because previously we're using that from PyTorch. And then we are creating the logistic regression logreg function. And then we're using the NN module as our base function as such. So we have to initialize the self and also initialize that mod and then the module, which is the super initialization. And then we get that layer with weights and with the biases. And see my slides. If I do that, try to do that. Okay. And then the definition of function forward, which is a PyTorch way of dealing. I'm going to mute you guys. If anyone wants to talk, just please unmute yourself. There's some noise in the background. I hope we can do that in some way. First, disable presentation. Right, remote control, no, rotate, manage participants, mute all, allow participants, yes, okay, thank you. Right, so so the forward function, which is the PyTorch way of kind of dealing with the gradient. I can still hear that noise. That's better. Okay. So anyone's got any comments on the forward function? Not something I've used like every day, so not that familiar myself. The way I understand, so you need that function so that the PyTorch knows how to track gradients on which functions. So once you define the forward, it's going to kind of call that function every time you go through your network, like once you load your data. And then it's going to use that for your optimization, whether this is SGD or ADAM optimizer. So in that function, we have the view is the way for PyTorch to reshape the tensor. So it's like the NumPy reshape, I believe. So the equivalent of that in PyTorch is view. And then there is this our function, so AX plus B. So we have the matrix multiplication of our X and our weights. And we also add in the bias, which is the L1B. So that's our linear layer. And then the next one is our nonlinear layer, which in this case is the, excuse me, the log softmax. And then we return the EX. Any comments on that? Any questions? Any corrections to what I've said?
Michael, actually, you mentioned, I think this is for PyTorch to do forward propagation, right? Not backward. Because it looks like it's just straight, basically, multiplication of, going forward.
Yeah, that's what I understand. But also, I remember Jeremy mentioned that you need that forward function. So PyTorch also could track potentially the gradients if you wanted to. But maybe I confused that with something else.
Yeah, I don't remember.
Okay, we'll find out later because I think later he's doing the gradients. So we'll see. Yeah. So then the next thing he's creating the net.
Sorry, Michael, just one more question from me. If you look at the softmax function,
yeah.
So I know the softmax is e to the x over the sum of e to the x. That makes sense. What doesn't make sense to me is this bit at the end where you've got this, colon, comma, none. Can anyone explain what's happening there?
So let me see.
So basically the last bit of what you softmax function.
Yeah. So so he's talking about the nonce later in the video. He was not necessarily explaining that here as well. I think he's making that that tensor to the size that he needs. So he's adding one more. So like if that was without that last part, that would be, I'm just thinking out loud. So he's got the torch exponential, torch sum on dimension 1, and then so what I think he's doing, he's getting that that tensor to the right shape. I'm not sure why he needs that particular shape. There must be a reason. Softmax. So normally he would need that as 10 to 1. So that would be just like a tensor, rank 1 tensor with 10 digits to my understanding. So why he wasn't getting that with this equation? Yeah, interesting one. I'm not so sure again. Something we could look again into. We could run this on Coggle kernels and remove that bit and see what we get. Maybe we can do that later if we have enough time. But to my interpretation, he's making this the right shape. But I don't know why he wasn't getting the right shape in the first place.
Sure. Okay. Great. Thank you.
So with that softmax function, what he gets. So if the x, he just gets what? He just gets one number, right? Or she gets 10 of them because he needs 10 at the last layer. Okay, maybe we can run that in kernels to see how this works. Anyone else got any ideas why we have this colon and none there? I'm also checking on chat now. So you can write, you can talk, you can... Nope, I don't see anything. Okay, well, maybe we could come back to that later. It's a good question. And then he creates the net2 and puts that on CUDA. And using again the Adam optimizer. And then he also uses the parameters. And what I understood, Jeremy, that was also the PyTorch function. And then he can again use the fit function to calculate that that network. And then he started talking about data loaders. So the way I understand data loader in PyTorch is like, because we don't calculate all of the either stochastic gradient descents or the other optimization functions for the all data we have, we calculate that in mini batches. So for the PyTorch to kind of like keep feeding the network with the mini batches and calculate all these loss functions, PyTorch uses those data loaders. So the data loader would kind of give mini batches one at a time. And what he was saying, he was using like a combination of Fast.ai and PyTorch. He was still using the image data classifier from Fast.ai, which I didn't paste that into this slide. And then he was using the iter, so the Python iterator. So the data loader is the iterator over the MD, that's the data, and the trading data loader. I believe that's the Fast.ai, the data loader for trading data. That there are more iterators Jeremy showed. You can use this on training, on validation, on test data. So that's yeah. So the next function, if you use that on the data loader, is going to kind of give next batch at a time. That's my understanding again. So he assigned that to X mini batch and Y mini batch because that gives you the dependent and independent variable. And then he's also using the variable function, and that's from PyTorch, I believe. I think, if I remember right, what he said. And that variable is going to convert that tensor into such a construct that maybe that was the one that it needs that one to kind of keep track of those gradients. I believe maybe that was the one, you're right. So not necessarily the forward function, but the variable. I think that was it. Do you remember the same, that the variable is needed to kind of, so that PyTorch can keep track of all the function that was used to create the that and that loss, so then it can calculate the like gradients or other optimizers on that function?
Yeah, I think that's what basically it adds derivative to the tensor.
Yeah, that was my understanding as well.
Okay.
Yeah. So then he gets predictions from that. What is the VX MB? Oh, that was the variable. Okay, from that. So he uses that to get the predictions, and then he plots just 3 lines, 3 rows of the prediction. So as we see, we get like, so what we're looking, so the prediction here, like the digit on the image will be the highest probability. So once we get the predictions, we need to find out which one of those is the highest. So if we look, we have -3, 10 minus 5, 10 to minus 5, -2, -5, and -1. So from that row, the last one, which is 9.74 times to -1, this seems to be the largest one from that row. So then we need to, yeah, that's only 6 columns. So the next one, -6, -4, -3, yeah, it's still that one. So then we need to find out which one that is from that big tensor, and for that, no, he didn't show that here, but for that he used the Pratts Max. So the max is the PyTorch way of like NumPy argmax. So the max 1 is going to look for the 1 is like the columns. So it's going to look for the maximum across the columns, and then it's going to return that value, and also it's going to return the location of that number from 0 to 10 on location in that tensor. So because in this case, we just need the, we need the location. So we choose again 1 in square brackets. So then it's going to give us the predictions like 6, 7. So this is the digits. It is predicted based on those 28 by 28 images. So so also in this slide, what he did, he added one more hidden layer. So from the shallow network that he created initially, just one linear layer and one nonlinear layer, he added another linear layer. So now we have the first one is the 28 by 28 and 100, and then nonlinearity as a ReLU, and then he added another linear layer of 100 on an input and a 10 on our output, and then the last one is the log softmax. So there was a question, why is 100? Why if it goes from 784 to 100 and then from 100 to 10? And I think the answer was because it was just easy for him to add 1 0. But yeah, that's interesting because you could create like 1,000. I wonder if the result will be better. I guess it's easy experimentation, but just thinking about it, why would be we go 10, 10, and 10, or from 1,000 to 1,010. I'm not sure. That would take more time for sure if that was the larger number. But I'm not so sure if that would be a better result. Maybe, maybe not. I think I've tried once, like going crazy with the layers and crazy with how big the layer was, and the result wasn't that great. I don't remember now exactly what I did, but I was playing with the data. So I've made like maybe 10 layers and like thousands or even 10,000 per layer, but the results didn't get better.
Michael, did you try smaller than 100?
Yeah. I don't remember now. I was some time ago when I was playing with that data. And I remember that the result didn't get better when I was added like 10 layers and I've made even the much larger. So
yeah, I think that Jeremy spends a lot of time tweaking things, and so usually the things that he puts in are the best.
Yeah, that's right. Yeah, yeah, I'm not sure. So this is the I guess maybe it's not. Yeah, maybe it's not about the size of the layer, but for sure here adding the second layer helped a lot, right? Because he was able to get like 5% better result. So the adding the 1D player helped a lot, but I wonder if we just added, because I think I did. It's a shame I don't have those experimentations with me anymore. We could go to Coggle kernels as well and see how this how we can play with it. So let me maybe put that down.
Yeah.
There were two things we wanted to check. We wanted to check that from the previous slides, those why we use that softmax, the none thingy at the end, and then the second.
So Michael, are these, when you said you go to the Coggle kernels, are these all on there, or you mean that's just an easy way to try it out?
Yeah, it's an easy way to run the code, and then we put those lessons there, so they're available. So let's see. We should have We should have enough time. So we'll do that later, I think. So let me just. The second one, we wanted to do some experimentation with more layers. Yeah, for sure. We'll go we'll go to Coggle kernels. I show how to do it. It's easy. So yeah, so he created 2 layers, and then he got better result by 5%, which is great. And then he gets the predictions. Yeah, and then he started explaining how the in general how the deep neural network is constructed. So then from the input, we get to the linear layer. So this is the matrix multiplication. Then we need nonlinear layer, and then another linear layer, another nonlinear layer, and so on, so on, so on. we could be adding those layers as we want. That's our kind of design decision. Though the in-between layers, the nonlinear layers, are either ReLU, which is basically 0 for numbers that are below 0, and a number for, say, call it x. So if the x is less than 0, it's 0, and if the x is more than 0, it's x. Or the leaky ReLU, which is not 0, but going like a little bit into negatives, or LU. But to what he said, like, doesn't really matter as such. So I think through the whole course, Jeremy is using ReLUs. Even if deep learning course, I think it's also all ReLUs. And then the last layer is softmax or sigmoid. So softmax will be for the if you have just one label per image. So like in our MNIST example. So that softmax is the best to use. And then if you have like more labels per image you want to predict. So the example he was giving, like if there was a picture of a cat and dog, and you wanted to predict that you have label cat and label dog for the same image, then the softmax is not the one to use because it's going to favor just one over the other. So the sigmoid is the better one for that particular case. Then comments, questions on that slide?
Or you could, I guess you could use the softmax and just have like a threshold, right? You can say anything above 0.2 or 0.3.
Yeah, potentially. So you say instead of using sigmoid, you would use softmax with a threshold? Yeah, I think you're right. So I think there is such a, yeah. So when I was doing one Coggle competition, and then you were predicting, yeah, so there were images, and then you were predicting labels for that image, and they could be, sorry about that, and they could be like even hundreds, if not more labels on some images. So you're right, you would set a threshold because the neural net is going to give you predictions for all labels. So say if you have 2,000 labels in your whole data set, it's going to predict on every single image those 2,000 labels. So then you're right, you would give like a threshold that, because you don't want like predict 2,000 labels and submit that to Coggle because you will get poor score. So you want to set a threshold on some level, after which the labels will be ignored and only above certain. Yeah, you're right. That's a good point. I wasn't sure.
I'm pretty sure that's how they do it. I mean, for multi-label problems with using the softmax.
Yeah, yeah, makes sense. You're right. Yeah, yeah, and yeah. So then you set So then you set your threshold. Depends on how many labels as such you want. Of course, if it set the threshold higher, you get less labels that will be more accurate. And if you set like lower threshold, you get more labels, but they will be, some of them will be less accurate as such. And
yeah, and the threshold itself determines how many labels you get. I mean, so like you set the threshold, and then you step back, and then for each image, it will have however many labels passes the threshold. You know, so some images might have 3 labels, some might have 10, some might have 1, depending on the threshold.
That's right. Yeah, good point. There's a question or comment on the chat. I'm also monitoring chat there. So then that 10 might be the number of labels that can be identified in an image. Yeah, yeah, correct. So the 10 is the number of labels. In this case, we have 10 digits from 0 to 9. That's why we have the 10. Yeah.
Right, and in this case, we only want the one with the highest probability.
Yeah, and in this case, we just know we have only 1 digit per image, so we only want 1. That's correct. Yeah, yeah. Then Jeremy started talking about performance. So if we wanted to, because we can create the same thing in different ways, so we can use like for loops in Python, or we could use the, in this case, PyTorch, and then you can use PyTorch run on GPU, so PyTorch.CUDA. So he's saying that if you use just for loops in Python, you're going to get like, because the PyTorch is actually implemented in C or C++. So just comparing that, you get like 10,000 of a difference by a factor of 10,000, which is huge. And then by using the SIMD, which is the single instruction multiple data kind of way of instructing GPU a processor, which could be GPU, you get another speed up, and then you have multiple cores in your processor, so you can also take advantage of that. So you can get like 32K, the speed improvement of factor by 32K, which is huge. So I think that was interesting to show that especially if you have a lot of data, then that matters. Yeah. So again, any questions, comments before we move to the next slide? So it's like, nope. So let's move on. And then Jeremy introduced the broadcasting, which he said is one of the most important things that it's used in deep learning. And he's also referred to the another training Fast.ai have, and it's taught by Rachel, and that's the computational linear algebra, I believe, where the course is based on, especially on those things, how to compute a lot of numbers on CPU, GPU using like NumPy or PyTorch or other stuff. Anyone did that course just out of interest?
No, but I'm thinking of doing it during the interim between the next, between now and the next, in the Fast.ai deep learning version 2. I mean, sorry, deep learning part 2.
Part 2, yeah. Yeah, so many things.
Enough time, I think.
So many things to do, not enough time. That's right. I just looked at that course. I think I just watched one lesson. It looks very good. I mean, I would love to do it, but same boat as you, just time.
Yeah.
But, yeah, they also kind of refer to this 3 brown, 1 blue kind of videos that are on YouTube. They kind of explain all the matrix multiplications, all other stuff. So for sure, quite interesting. But yeah, so he started talking about broadcasting and why this is so important. I guess again to get a speeds up of calculations. So like in this case, he created an array, which is A, which got 3, which is array of 3, size of 3, which got numbers 10, 6, and -4. And then when he checked whether the A is greater than 0, so 0 was just one number, a scalar. So he's comparing vector to a scalar. So the broadcasting, what it does, is, the way I understand, again, that's my interpretation, paraphrasing Jeremy, is that you can still do that, and it's kind of like copying that 0 3 times, but it's not really copying that 0. That's why it's so fast and doesn't take the memory as such. It's using some Python functionality, and I believe that's pure Python in this case. It's not PyTorch. Maybe I'm wrong. Maybe it's
it is Python, and it's kind of like it does exactly what you want it, what you would want it to do, right? I mean,
yeah.
If you ask if A is greater than 0, you want it to actually check each element and give you a result like that, and so it's a really nice feature.
Yeah.
And if you have like a 2-dimensional array and you ask it to add a column vector, then it will add the column vector to each column of the array.
Yes, I didn't copy. Yeah, that's right. I didn't copy all the slide, all the examples there, but I think I just did that one and the other one. the other one he showed like how to broadcast a vector to a matrix. So in this case, he's got a vector size 3 again, 10, 20, 30, and he's multiplying that by a matrix 3 by 3, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So what the broadcasting would do, it would copy, quote unquote. It's not copying; it's just kind of like copying that that vector 3 times. So we get like 3 by 3, 3 by 3 matrices. So we can do that calculation. Yeah.
But I would think that in this case, it's like if you look at that matrix product, if you do the dot product, that would give you a vector of length 3 if you just do the dot product. Yeah. But I think if you broadcast it, it assumes that you want to do element by element. First, it blows up that 10, 20, 30. It replicates it to a full 2-dimensional array, and then I think what it does after that is it just does element by element multiplication.
Yeah, I think in this case, it's maybe even addition. I'm not sure which one.
Oh, addition. Oh.
Because on this page he's got multiplication, right? And then below it's got addition. So it's m.
Oh, okay. Yeah.
So it's m plus c. Let me see. So that was m. That was c.
Yeah. It's gonna just So it first makes it into a 2D matrix and then it adds them together. Is that?
I can't.
Yeah, I can't see the.
Yeah, you're right. It's you cannot see that well. I think it's m plus c what he's doing there. Yeah.
Yeah, it is.
Yeah. And then also a definition from the NumPy, what that means. I'm just going to leave it for you guys to read it later. And then he starts writing the training loop like without using too much of anything, just pure Python. I think he still uses some of the PyTorch, like the variable and the data loaders. I think that's the only thing that he is using as such. So he creates that data loader. He gets that xt and yt, gets the predictions. He defines the loss. Everything is on GPU. And then the logistic regression is same as it was before, I believe. And then he's using the optimizer. Okay, so he was saying that he needs to like 0 gradients before each backward pass. And then he does the backward pass, L.backward. And then he's using the optimizer step to find out the, I wasn't sure, to find out the minimum loss or just to do one step.
I think it's just one step.
Okay, yeah, so just to do one step. And then he drew this as picture of a simple function, which is and then on the y-axis we have loss, and then on the x-axis this is our x. And then we start somewhere randomly, and then yeah, it's quite messy, this picture actually.
Hey, so why do we zero out the gradient at the top?
Yeah, I think I didn't really get that either, but what he said was that it's kind of PyTorch would not zero that for you, so you have to do it manually as such.
No, but why are we doing that?
Because you start in the new, so you want to calculate those gradients, and so before you calculate, you zero that. But why? I wasn't sure either, but I guess this is what the procedure looks like. Maybe if you didn't zero them, they would be not zero, and that would confuse the PyTorch in calculating the new gradients. I wasn't sure either. It seems like that's the kind of procedure how to do it. So you zero them first, and then you calculate them, and then you just get the one step. He didn't explain here. I'm not sure. Anyone else got better explanation than I have? Why do we need to zero the gradients first? I'm also checking chat. Don't see that either. I guess just trust Jeremy in this case. Yeah, so also here he started talking about learning rate. What's learning rate? So the learning rate is the, so say we by randomly, we start somewhere here. I think that's where he started. So then we want to find out a better, smaller loss. So we want to go in the direction where the loss is smaller. So we create the gradient. So we know the direction now to which we need to go. So if the gradient go this way, so we want to go this way. And then we calculate that derivative, and then we multiply that by a small number. And in this case, he chose that small number to be 0.01, and that's something what's called the learning rate. And there is a whole lecture on how to find out the, well, not the whole lecture, but there's a part in a lecture in a deep learning course on how to find out what learning rate should be used for the particular data set and particular network. And the Fast.ai library, they've got this learning rate finder, which is based on the, I believe, Leslie Smith's paper about how to do it. So basically, you don't want to choose it too small because you will go very slowly to the lowest loss. And also you don't want to pick it too large, although you would go faster, but it could go in the wrong direction and never find the minimum. Yeah. Any questions about learning rates or this slide? Comments? Nope. Yeah, and then he just continued creating the training loop with the for loop. So, and then with every 10th iteration of that loop, he was printing the loss and accuracy. So we can see that after 10 iterations, we had 0.2, and the accuracy was just increasing to 0.875 after hundreds of iteration, after 100th iteration. And that's what I had on slides. So if there are no more questions, we could try to see if we add more layers, for example, in a Coggle kernel, for example, if that's going to work. Can you see my screen now with the kernel?
Yes.
Cool. I think I need to make it run. I need to fork this notebook. Let me
We
see.
should put the link for where these notebooks are for everyone on the
Yeah.
chat. Maybe I was trying to find it, but I forgot where it was.
Yeah. So let's see if it's going to work with us today. I hope so. I just need to move that somewhere here. So, still working on something. Okay, now it should work. So I don't want to change that. I want to just go to whenever that. So I just need to load the libraries. So let me do that. I want to set my path to the data. I want to do that, I guess. I want to get the data. Okay, which is this. Okay. So now we have data. We have 50,000. We have 50,000 digits in our training. Yeah, so we have 50,000 images in our training. So then we want to normalize them. So that's this. Now we want to, well, actually this is normalization as well.
Yeah, we're normalizing the validation set with the same numbers we got from the training set.
Yeah, you're right. The first one was for the training, and then we use the training kind of statistics to normalize the validation set. You're right. Now I need to just, this is some helper functions to plot that things.
Yeah.
So we could plot those, or we can go straight away to the neural network, which is somewhere. Okay. Yeah. Okay. So let's maybe import torch as well. Okay. Right. So now we have our 1, 2. Okay. So this one actually has got 3 layers. So it's got input layer, then a hidden layer, and then another layer. So that's that, and then let's get our data, and then let's see what the result will be. And for that, let's run through that code. Fitting the model. Okay, so let's fit the model. It's going to do 5 epochs. Shouldn't take that long. Come on. Okay. So already first one gives like 0.92 accuracy.
Wow, not bad.
Yeah, not bad. Yeah. And that's using the default learning rate, which I don't remember what that was, but there was something, I guess.
Was it 0.001 or?
Possibly, yeah.
I thought that was the value you had said before.
Yeah, I don't remember I've said it, but okay. Okay. Yeah, it takes more time than I expected. It's maybe Coggle is like slow today. Okay, so that's last one. Okay, so we have like the 0.92 for after last epoch. So if we now, where is the code? Where is it? Oh no, it's not working. Great. That's what I wanted. I just want to wait, maybe I click. Because I wanted to play with, okay.
There it goes.
So so I can do 2 things. I can increase that network, but it's going to take more time. So I can do that. So I'm going to make it like 10 times bigger, larger, that on this direction. So I could make this larger as well.
I would just do 1 because
just 1. Okay.
It's going to be longer by a factor of 10, and then if you do 2, it'll be longer by a factor of 100.
Yeah, I'm going to run like 1 epoch only. Okay, so let me change that. So let me now run it, and then I go to that. I'm just going to do 1 epoch, so it's not going to take too much time. I see. So now our network is 10 times bigger, 10 times larger. Let's see if the score is better. If it works. Right. It's actually not that good. Maybe that's interesting.
Maybe it just needs longer to train or something. I don't know.
I'm going to change it back to what it was because that's interesting. I didn't expect that.
And then what happened if you make it 50 by 50? You know, like instead of 100, make it 50, and wondering if that would be so much worse.
So I just moved it back to what it was, the 100.
Yeah.
Let me see, because I didn't expect that.
Make sure we got back what we had.
Yeah.
Oh.
Okay.
Something wrong.
Something broke. Let me see. So I have our my network. Okay, so I need to run more code, I guess. So do I need to get another data set? It's not using network as such, but let me do it anyway.
Yeah.
let me do that as well. Let me do all the things that are here. Now let's see what we get now. It was like 90%.
Yeah, 92% was what we had.
Yeah. Yeah.
There we go. Okay, we got it back.
Okay, so now let's, oh man, doesn't work again. I hate it. It's maybe because I'm using Firefox and it doesn't really maybe work that well with Firefox. So if we just increase it by 10, size it's factor of 10 now, and then let me run the same parts of code again, just to make sure it works. Let's see. I think that must be my Firefox. Yeah, so it's not better, right? Is it?
It's better or about the same.
It's about the same, yeah. It's not 10 times better, right?
Yeah, right. Now let's wonder what happens if you do 50 instead of 1,000.
Yeah, so let's make it smaller. So we're going to make it smaller. You're right. So let's make the first layer smaller. So the next should be also 50. So let's try that. So let's run this and that, and that, and then just one more, one epoch. Let's see.
Oh, not too much worse.
Yeah, we can. So if we go back to our 100 and if we add like more of those, so we're going to add. Come on. That's what I wanted to do. Let's add like 1, 2, 3. So 3 more layers. Which you think about it, it should be better, right? But maybe not.
Yeah.
I don't know. The bigger is better, right? So, so the bigger network. Let's see. Let's see if that works at all. Okay, let's try to use one epoch again. Yeah, it's not better, right? So, so yeah. So this is what I also found when I was doing this like some time ago. I was trying to make it bigger network, more, and also more weights as such. And yeah, there's something else you have to do to kind of make it better. And
You know, it's just an interesting thing to think about, although I have no answers. But I mean, like, what is the optimal size of the network and how many networks? You know, the optimal sizes of each layers and the number of layers that would give the best best answer with the smallest training time.
Yeah.
It's an interesting problem. And I think they're having these new startups that are trying to do like automated machine learning where they try to attack just that problem with somehow kind of optimization or neural net techniques. They try to determine, you know, automatically what the right network size is.
Yeah.
I think that's the next step in the future. That's what we're going to see in the future. And then it'll be like everybody can do machine learning and you don't have to know anything. You just push the button.
Yeah, that's right. It's similar to the platform.ai that Jeremy showed in the last deep learning class, right?
Yeah.
That you can do some image classification without putting any single line of code, actually. So I think that's what the whole thing is going into. That's the direction. I think that's what. So I agree. Okay, so 1 o'clock. Are there any questions, comments?
Hey, Mikhail, could you try out, you know, there was that function we were trying to see what the input was expected. Can you run that on the Kaggle thing while you've got it out?
Yeah, that's right. That's right. I forgot about it. That was the definition with the softmax, right?
I think it was, yeah, I think it was the softmax function.
Where was it? So now at the top. That's our data. That's the show. Where was it? It shows PyTorch. That's the with PyTorch metrics within the model. Okay, I think it starts
There
here.
you go. There it is.
Right, that's the one, right? So let's. So if we. So what we want to do? We want to copy that and paste that. So now we just copy the one. So if we remove that one, and then we run it, and then I guess it's going to complain somewhere about the size of yeah, it's complained. So I think that's why Jeremy used it, because it was needed. So it says the size of the tensor. The size of a tensor 10 must match the size of a tensor B64 at dimension 1. So I think that's why he did that. So he changed the dimension of that tensor by adding this, because now it's complaining that the sizes does not match. So he used that for the shape, for the size, and the nan is adding that like a dummy dimension as such. So it's not, I think it's like adding ones or something. That's the way I understand it anyway. So if I add it back, I think it's going to run now. Yeah, now it works.
Can you make it print the shape before you take the like before you select the colon none element? Can you make it print the shape or?
Yeah, let me try.
See why it's doing that. I'm not sure how to do that. Let's see.
Oops, do you copy again?
Softmax definition.
I didn't want to copy it. Okay, let me. That's really my. Right. So what do we have? So we have. So okay, that's just definition of a softmax, and then where are we using this softmax? Because we cannot get the shape here, right? Because
inside the definition, maybe.
So I think what he means is, so don't do a return thing. So make that a variable, print that variable, and then return that as your.
You mean print softmax?
Yeah. So you got def softmax, right? And then you say y equals, and then all of that torch x and so on, and then you do and you say print y dot shape, and then you do a return y.
So guide me. So you mean type
sure.
like soft?
So I'm guessing what he's saying is, so you within your def softmax x, right? Then you say y equals, and then torch x, and basically what you're returning as your softmax function, and you assign it to a variable y, and then you do a print y dot shape.
Like this?
No, I think you're going to do it in softmax, right?
Start out with the softmax definition and then expand it. Instead of doing Jeremy's stupid thing where he has to have everything on one line, just expand it out so you can.
You mean here?
Yeah. So within your thing, yeah.
So, okay, guide me. So what I have to type?
So within softmax, say y. So for example, take everything that's after return and put that. So take everything that's after return in the softmax, right? And then you put that into variable y. Say y equals that.
First, make a space after the colon and definition of softmax. After the space, just hit a hard return.
Yeah.
so you can expand that function. So right after def softmax x colon, right after the colon, put a hard return. Yeah, now you can expand that definition and do some stuff with it.
Okay, so then basically just delete or just put a comment there, or you just put a hash.
Where is it? Where?
There, exactly where you are, where your thing is. No, where your cursor was before. Basically where that return is.
Here?
Yeah. Right. No, on return, on the left of return,
Here?
where it says return.
Yeah.
Here?
Yeah.
Make it a comment. Make it a comment.
Yeah. Okay. And then you say y equals that, and then you say okay. So then you say y equals that, right? That's right. Then the next line is print y dot shape. No, y dot shape, as in it'll have to be y dot shape.
So it's not print, it's just y.
No, sorry, it is print, and then in brackets y. Yeah, okay, and then just nope, no brackets after that. So print left bracket y dot shape close bracket.
Print.
Yeah, left bracket y dot shape. Yeah, okay, and then the next line is return y. And then obviously you have to indent all of that because it's not going to work. So indent all of your stuff.
Yeah.
Okay. So executed that line, but didn't print any shape as such. Yeah, so it need how to find out that shape. So it's using that the softmax, it's used here in a forward, and the forward is executed when you get your feed. So it's here, as we saw, because it broke somewhere there. Yeah, I guess we need to play a bit with this a little more. Why he needed that shape of that that particular shape? Maybe something we can talk in the next if we remember. Let's remember. Maybe
you can put pass after the print, so it stops there.
Was that?
I think after print, if you put pass, that stops the execution.
Like that?
On the next line.
Next line. Okay. Yeah. Like this?
Yeah, and then you can just run it, and it will print the shape.
But I think it doesn't have any shape yet because it's just definition, right?
Yeah.
So it needs to use that function, and then you can do a shape, because now it's just definition. So there is no shape. It's just definition, right?
That's right.
Yeah. So that's why I'm trying to find out why it's using that, and it's using that in forward, but it's still definition. The first time it uses that is that fit function, I think.
You know what? I think what would be easiest is if we don't try and do this as part of the neural net, but instead you have the input, you put in an input as one of the tensors, and then you just run that softmax function itself rather than the whole neural net, because that's what's giving us a problem.
Okay. So we have.
But what is our input x there? So that's going to be.
So we just run softmax, and then we need x.
Yeah. So if you could figure out what x would look like.
And that's the data loader, I guess. So it just gives your data, iterator of your data loader. That's what it's used on. So you want to use softmax. Softmax you would use on a tensor rank 1, I guess. Yeah, on a tensor rank 1 you would use. So if you use like this, I guess 1, 2, 3, 4. It's not a tensor, right? It's more like an array. Yeah, it's complaining because it's not. It's a tensor. It's not a tensor. So to make it a tensor, you need 2 brackets, right? Let me see. Okay, I need one more. No, must be tensor, not a list. Okay, let's create a tensor. So let's say A is our tensor. how do we initialize tensor if we say like 1, 2, 3, 4, and then let's do that on, I believe that's now a tensor, that's now tensor. So now let's put that tensor here. Still doesn't like it. Torch kill that long tensor. Okay, because it's not, we don't want long tensor, I guess. We want we don't want long, we want just int, right? So we need to change that to, we want to change that to int in some way. So it's like this, the type. That's more like NumPy, right?
Yeah.
Let's try if tensor works like this as well. No, it doesn't. Okay. Yeah. Almost there. It doesn't like the, let's see. PyTorch, change. Torch tensor, data type. Okay, there's something there. So we want, what do we want? We want floats, I guess. I'm not sure what he expects. He didn't say what he wants, right? He just said that it's not implemented for the long tensor. So we could try with a float, I guess. Now, how do I change the float? I tell
you what,
okay.
just why don't you just grab the torch zeros and see if that works for us?
Yeah, so I think when I initialize the tensor, right? I think that's what it was. Let me see. Does it work like this? No. Why not? You like zeros like this? Okay. But then
yeah, just try that whole line and let's see if that creates what we want.
Yeah, he will not. He will not like it because it will not like it. But let's try.
Oh.
It will not like it. So if I say this is my A, and then I want this. Yeah, the int tensor doesn't like int tensor as well. So what does it want? Let's try the float.
64, yeah.
Yeah, I like that too. Let's see. Like this. No. This, but say I want like 10 zeros, right? Something like this. Out of range, expected to be between, okay. Okay. Say it expects -1 to 0, but it got like more stuff. What do we get? We got all zeros. Dimension of the expected range to be in the range -1, 0. That's interesting. I go 1. Where's the 1? Well, the softmax, I guess, is 1. Yeah, so if everything is 0, I guess softmax could be. So it's just random. No, it doesn't like random as well. But at least it likes the floats. Interesting. Okay. It's expected to be -1 to 0. Interesting. I don't know why it doesn't like it. Very close.
It's expecting log probabilities. So why don't you put -rand or how it wants the number to be between -1 and 0. So multiply the whole thing, a equals -1 times, maybe, I don't know. Maybe that'll work.
Like this?
Yeah.
Okay.
Still didn't like it.
No. It's picky. It's a softmax. It's a very picky function. Not sure.
Dimension out of range. Oh, it says that dimension out of range. I don't understand that. How can a dimension be -1? Or how can it?
Okay, so you're saying that the
I don't know. Yeah, maybe make it 10-1 or something. 10. Maybe make it rand to 10,1.
Still the same issue. At a dimension.
No, rand of 10,1. So it has a dimension of 10,1. Comma. Yes, comma 1. Yes, maybe that'll work.
Oh yeah, right. Here we go. Nice one. So it gives a softmax. So that's what we wanted, right? So we wanted to check the.
How come it's not printing out the our print statement?
We wanted shape, right? Is it like this? No.
Well, we wanted it to print inside the softmax, and it's not doing it, right?
Yeah. So the shape is 10-1,
Yeah.
and now if we change that.
When we call softmax, we should get it to. It should print because you redefined softmax, right?
No, yeah. Oh, yeah. I thought you had.
Yeah.
I think I didn't use that one. So so if we remove that one, so let's see. So now the shape is 10×10, and we need 10×1. That's why I think he's using that none thing, because I just removed it and the shape now changed to 10×10, and that's not.
Yeah, I think I looked. I put a link on the group chat where I found in Stack Overflow. It says that when you use none for a dimension in Python, it means to omit that dimension or to skip it or something. So I think it's the same thing as choosing the first element or something.
Yeah. So when it gets a tensor to a softmax, it kind of creates a rank 2 tensor for some reason. That's how the way it works. So it returns. Okay. Yeah, that's interesting.
Yeah.
Yeah, so now with the nan, I can run it again. It's going to, yeah, so now the shape is 10-1, where it was 10-10 without nan. I guess we're closer there, but maybe still need to.
We're still not quite sure why that syntax is there.
Yeah, that's right. That's right. Mm-hmm. Okay, that's maybe something, some homework to do before next meetup.
You know, if you had a vector of length 5,1, and then you chose, and then you did that same thing, and you asked for just that vector everything, but with the same syntax, then it might return a vector of size 5, comma. You know how they do that in Python, where there's dimensions could be 5,1 or it could be 5, comma, and then it's different.
Right.
So I bet if you define a vector of some, just define a vector of length 5,1 and then put that same syntax on it, it doesn't even have to be torch, because this is just a Python syntax, not a torch, not necessarily. So yeah, make a vector of length 5,1. you know, zeros of 5-1 or something like that.
I can do torch again.
Yeah.
Torch and almost like this.
Yeah, and then
5-1, you said?
yeah.
I guess it's like this. Is it?
And then see what. Oh, and you have to put D type torch. Do you have to define a type?
This?
Yeah, and then you don't need to define a type, or okay, that's fine. So now ask for B square bracket colon slash comma none, and see what it does. Oh.
Interesting.
Okay, well, ask for the shape. Let's ask for the shape of that thing.
Of this
And
thing?
then, yeah, the shape, what's the shape? 511. Oh, it added it. And what's the shape of the original?
5-1.
Oh, interesting. So it added it.
Adds.
Added
It
a
adds.
dimension. I thought it was
adds.
going to take away a dimension.
It adds like dummy dimension, I think. Something
Yeah.
like that. Yeah.
Yeah. Interesting.
Yeah. So I think that what Jeremy showed, like you can use like this, and then you add another.
I see. Okay, so that's what that none is doing. It's adding an extra dimension to maybe to make the dimensions compatible with something else that it needs to interact with. I don't know.
Yeah, looks like it. Yeah. So it's adding another dimension here.
Yeah.
For some reason, which we don't fully understand. Yeah. Well, I guess some homework.
Yeah, that was really interesting to do. I mean, now we know what it does at least, and now we have to figure out why it does it.
Yeah.
Why he does that.
Excellent. That's nice. We have those kernels then, so we can just quickly play with them.
Yeah. So Michael, what's the link to get to those kernels? Because I forgot.
Oh, the link. Yeah. I just. So. Oh man, I cannot see my. How do I get rid of that thing? I don't know. Like this. I go to Coggle. When it gets there.
Fast.ai or?
Oh, I just look for your name.
Oh.
Because I know you did that one.
Uh-huh.
And then it shows me the lesson 4. And then I'm there. So this is the link.
Okay.
So let me post that into chat. Oh, yeah. Okay. Yeah. Is there? Okay. It's this one. Excellent. So thanks for doing that. It's a nice kernel.
Yeah. Well, thank you for giving me the idea. I just thought it was cool to be able to play with the Fast.ai kernels without spending any money.
Yeah. Yeah. It's free. It's free. Okay, excellent. We're 20 past 5:01.
Yeah.
It was worth the extra effort, I think.
Yeah, for sure. So next week we doing lesson 10. I'm going to post the presentation slides in the Slack channel, and yeah, we'll meet you in 1 week.
Are there any more, Michael? Are there any more notebooks, or is this all the notebooks are already there?
That's everything. So there were 5 notebooks. So I think next lesson, potentially he's going to introduce this NLP, which is on the last notebook.
Oh, okay. And they're already on Coggle.
Yeah. So everything's now on kernels. Okay. Excellent.
Thanks, Michael.
Thanks, Michael.
Thank you very much.
Appreciate it.
See you next week.
See you next week.